Now we've gotten quite far with linear regression, but recall that we only make point estimates when running our linear regression estimation. Today, I'm going to introduce the Gaussian processes, which give you a density around your estimation. And with that, you can give confidence intervals for your estimation. And this is the second to last lecture. In the final lecture, I will illuminate the strong relationships between Gaussian processes and the kernel formalism that we've discussed in length by now. So first, I need you to recall what a multivariate Gaussian distribution is. So we have a random vector x, and it is distributed according to a multivariate Gaussian density, which we will denote as such. So here's our mean vector mu and our covariance matrix sigma. And mu has n elements, like the random vector x. The covariance matrix sigma is a n by n matrix. And in it, we store all possible covariances between the vector entries of that random vector x. And x being distributed according to a multivariate Gaussian distribution leads to the following density. So it's the density of that random vector x parameterized, so this is the semicolon here, parameterized by the mean vector mu and the covariance matrix sigma. So here we just have a normalization constant. Let's not look at that just now, but instead let's investigate this exponential. And in this exponential we have -1/2 times this vector x minus mu transpose times the inverse of the covariance matrix sigma times that same vector again, x minus mu. And recall that the 1D case looks like this, so the normal distribution for a univariate random variable x looks like this. So we have this normalization constant times the exponential of this expression. So it's the negative of x minus mu squared divided by 2 times the variance sigma squared. And this is perfectly analogous to what we have here. So we have this -1/2 at the front. So here we have minus divided by 2, which is equivalent. And here we have x minus mu transpose times something times x minus mu. This x minus mu transpose x minus mu is like squaring this vector x minus mu. And this is what we have in the univariate case also, x minus mu squared. And this inverse of the covariance matrix sigma, in the univariate case, we have the inverse of the variance of our random variable. And this would be 1 over sigma squared, which we have here also. So this is the generalization of the standard normal density for multiple dimensions. And now I will give you a lemma, which will be very important for this particular lecture. So this lemma consists of a few parts. It basically states that this statement is true, and that the statement is equivalent to these two. So let's have a look. So the statement that we just assumed to be true, you will prove that in the exercises, is that sigma is positive definite. So the covariance matrix of our multivariate Gaussian density is positive definite. And the inverse of any positive definite matrix is also positive definite. You will also show that in the exercises. And finally, this expression where the middle bit is any positive definite matrix is a proper inner product. So let's have a look. So if we multiply any vector y transpose with that positive definite matrix, and then from the right we multiply any other vector x, then this will be an inner product of y and x. And the intuition behind that is we have vectors y and x, and the canonical inner product for these two vectors y and x was just y transpose x. And if we have like this diffusion matrix in the middle, which is positive definite, then this inner product between y and x will just be scaled according to this positive definite matrix in the middle. And since the matrix is just a linear mapping from one vector space to another, we have that a positive definite mapping from one vector space to another will lead to positive definiteness of this entire operation, and this will preserve all the requirements we have for an inner product. And again, since y transpose x was an inner product to begin with, the canonical one for this r to the d case, this will be also an inner product. Now, using this lemma, we have that this expression that we have in the exponential is also an inner product. So x minus mu transpose times the inverse of sigma times x minus mu, that expression is an inner product. And it's the inner product of x minus mu with itself, because we have x minus mu on both sides, and it is parameterized by the inverse of sigma. This is what I mean with this notation. And since by now we know that inner products induce norms, we have that this expression is equal to the squared norm of x minus mu, parameterized by this inverse of sigma. And lo and behold, this now looks like the argument of the Gaussian kernel. So maybe go back a few slides and look it up. We have that the Gaussian kernel was equal to the exponential of minus some constant times the squared norm of the two vectors that we want to compare in our kernel. And in this case, it's the realization of the random variable x and the expectation we have for x. And the intuition you should have for this is that large deviations from the expectations will have large magnitude and in turn large squared magnitude. And if this expression is large, then it's the negative of a large expression, and this will push this exponential to a small value. So large deviations from the expectation will be less likely than smaller deviations from the expectation. And this deviation from the expectation is parameterized by the inverse of sigma, and sigma contains the information about the statistical relationships between the entries of our random vector x. So for the 2D case, we have that sigma contains the following entries. So on the diagonal, we have the variance of the entries of our random vector. In this case, there are two entries, x1 and x2. And in the other entries, the off diagonals, we have the covariances between every possible combinations of entries. In this 2D case, there's only the combination x1 and x2. The covariance is symmetric, so it's the same entry on both sides. And finally, let's have a look at this illustration. So we have these values ρ. And for this 2D case, it's the covariance between the first entry x1 and the second entry x2 of our random vector x. Here's x1, here's x2. And in the case of positive covariance, we have that increasing x1 leads to an increase of x2 as well. And this relation is symmetric, which means that if you increase x2, then on expectation you will have larger x1 coordinate as well. So you will end up with this diagonal point cloud. And these rings refer to the standard deviations from the expectation, which is the center of this ellipsoid. So this is the point that we expect to draw. This is mu. But it's relatively likely that we draw any point within this red ellipse, because this refers to one standard deviation from the expectation. It is less likely, but still relatively likely, that we will draw points within this blue ellipsoid, because these are two standard deviations from the expectation mu, and so on. So this is the third standard deviation. And we see we have less and less points in this ellipsoid, because again, large deviations from the expectation, so this point mu in the middle, are less likely than smaller deviations. And here we have the same plot basically, but this time ρ is negative, so we have negative covariance. And this basically means as we increase one of the coordinates of our random vector, the other one decreases. So large x1s will lead on expectation to low x2s, and vice versa. This is symmetric again. Large x2s will on expectation lead to low x1s. The rest of this illustration is analogous to what I explained for this one. And here we have a covariance of 0. So the two features x1 and x2, they are unrelated. Knowing about one of the coordinates doesn't tell you anything about the state of the other coordinate. So you have this round shape. But again, you have these circles indicating the standard deviations from the expectation. And as you deviate from the expectation mu, which is the center, you will have fewer and fewer points. So let's review some basic properties of the multivariate Gaussian distribution. So for this, let's consider the 2D case. Of course, it will generalize to d dimensions, but this way it's a little more digestible, I think. So we have a random vector y. It contains of two entries, y1 and y2. We have the expectation vector mu. It also has two entries, mu1 and mu2. And we have the covariance matrix sigma. It has four entries. So on the diagonal, you have the variances of y1 and y2. These are random variables. And on the off diagonals, you have the covariance between y1 and y2. And now we suppose that this random vector y is distributed according to the multivariate Gaussian distribution, parameterized by this expectation mu and the covariance matrix sigma. And given this setup, we have three really important properties. The first one is that marginals of Gaussians are also Gaussians. So just to remind you what the marginal is, we want to find the density of that single entry y1, the first entry of our random vector y. And to find this, we take the integral over all possible values y2 could take of the joint density of y1 and y2 parameterized by mu and sigma. And this density will be a univariate Gaussian density again. And it will be parameterized by mu1, the first entry of our expectation, and the variance of y1, which is the first diagonal entry of sigma. Now I think this is really natural actually, because this is the expectation of your y1, and this is the variance of your y1. And these two values suffice to define a normal distribution over your entry y1. And it's nice that this is exactly the density that you end up with when you marginalize over y2, the second entry of your random vector y. Analogously to what I just explained, we have that the density of y2 is the integral over all values y1 could take of the joint density of y1 and y2, parameterized by these two objects. And similarly, intuitively, we have that y2 is distributed to a univariate Gaussian density, and the mean value is mu2, and the variance is the second diagonal entry. Now the second property is that sums of Gaussians are also Gaussians. So for this, consider this random vector x. It is distributed according to some multivariate Gaussian density, and there's also a second random vector y, and this is distributed according to a different multivariate Gaussian density of the same dimension. This implies that the sum of x and y, this vector, is distributed according to this very natural multivariate Gaussian distribution, where the expectation is just the sum of the two expectations, and this covariance matrix is just the sum of the individual covariance matrices of the individual arguments. So I think also this is a really nice and intuitive result. And finally, conditioning on Gaussians returns Gaussians again. So we have these two entries of y again, y1 and y2. And if we condition y1 on the second entry y2, then we have via Bayes' theorem that this is equal to the probability of y2 given y1 times the probability of y1 over the probability of y2. And if we write out this again, this is the joint of y1 and y2 occurring together. So this is the joint parameterized by this expectation mu and this covariance matrix sigma. And above we found an expression for the density of y2. It's the marginal over all values of y1 of the joint. So this is what we have here. So it's the integral over all values y1 could take of the joint density. And this is also Gaussian. This random variable y1 conditioned on y2 is distributed according to a Gaussian density, and it is parameterized by these two quantities. So it's getting a little messy. This is why I only wanted to consider 2D multivariate Gaussian distributions. So this random variable, the first entry conditioned on the second entry, is parameterized by mu1, the expectation for the first entry, plus the covariance of these two entries, times the inverse variance of that second entry, times the second entry minus the first one. So the details are not really important. We will not derive this result. We will not use it again, I think. It's just that you see that all the quantities involved are some combinations of those above. And similarly, we have that the variance of this object is equal to the variance of the first entry. And from that, we subtract this quantity. It's basically the information we have about the relationship between these two entries. So this is the covariance of the first and the second entry. We multiply it with the inverse of the variance of the second entry and multiply it again with the covariance of these two entries. So you don't have to remember this. I don't remember it myself. It's just for you to see that conditioning on Gaussians also yields a Gaussian again. And the main gist of this slide, what I wanted to bring across, is that all these manipulations on Gaussians return Gaussians again. It's all Gaussians. Okay, now let's return to our linear regression model. And in this setup we had that we assume that a label y is equal to the inner product of some feature mapped observation, where the feature map might be the identity, of some observation xn and the parameter vector w in some reproducing kernel Hilbert space. And since this bit is our prediction and we expect to make errors with our predictions, we include this error term epsilon n. And this is what we have here. So this is our model, our prediction, and we include an error term. Now let's make an assumption. And in practice, you would have to check whether this is indeed true. But let's assume that the noise follows an independent, identically distributed Gaussian distribution with zero mean and variance sigma squared. And in notation, it looks like this. So these epsilons are now random variables that we draw from a univariate Gaussian distribution where the expectation is zero and variance sigma squared. And we draw all these errors IID. This is a really strong assumption, so don't underestimate this. And now, having made these assumptions, let's calculate the likelihood of our observations given our model. So we have the density of our true labels, y, given the realization of our observations x and the realization of our parameter vector w. So in this scenario, it's a random variable. And this is a random variable because it's a function of our observations. So we fix these two random variables and condition the random variable of the true label vector given these two realizations. And since we made the IID assumption, this density is equal to the product over n observations of the individual labels conditioned on the individual realizations of our observations and the parameter vector w. And I just noticed that here's the index I, but it should be a small n. And since all of these terms are univariate Gaussian densities, we have the following product over n observations. We have this normalization constant times the exponential of this bit. So again, I have to change this to n. It's the negative of the true label minus the model prediction squared divided by 2 times the variance of our errors. So essentially, y, the true label, is drawn from a normal distribution where our expectation is our model prediction, and the deviations from our model predictions are our errors epsilon, and these have the variance sigma squared. So this is why we have this expression in the exponential. And then if we find this product, we have the following expression. So this turns into a multivariate Gaussian density where we have this normalization constant times the exponential of minus 1 over sigma squared times the true label vector y minus our prediction vector y hat. So this is actually our error vector epsilon underscore transpose times itself. And I'd like to remind you of the curious little fact that epsilon underscore transpose times itself is equal to the squared L2 norm of our errors. So this entire bit is the squared L2 magnitude of our errors. And if we look at this expression again, I already told you it's a multivariate Gaussian density, and this is parameterized by our prediction vector y hat, or in this notation, our model parameterized by w over all our observations x. And the covariance matrix is sigma squared times the identity. So this covariance matrix sigma looks like this. We have sigma squared on the diagonal and 0 covariance everywhere else. And this is because we assume the errors to be independent for each observation. And now, given the setup, we want to do Bayesian linear regression. And in a Bayesian framework, we need a prior over our parameter vector, so a density for our parameter vector w. And in this prior, we encode our beliefs about the parameter vector or the distribution of the parameter vector before having access to any observations. So let's just assume such a density. So we assume our parameter vector w to be drawn from a multivariate Gaussian density, where the expectation is the 0 vector, and we have some covariance matrix for our parameter vector w. So this is essentially the uninformed prior. We just assume a 0 vector as our parameter vector, which likely will not be true. But the beauty about the Bayesian framework is that we continuously update our belief of this density by finding the posterior. And the posterior is the likelihood. We calculated that just before on the previous slide, times the prior. This is this bit. And we divide by the marginal likelihood. And this posterior will then be our new belief about the distribution of our parameter vector. And concretely, for our context, the Bayes theorem looks like this. So the posterior is the density, the conditional density of our parameter vector W, conditioned on the true labels and the observations we have available. So these are realized. We have a data set and we want to find the posterior, the conditional density of our parameter vector W, given this information, our data set, right? So think about it. We want to find the parameter vector W. Previously, we have solved it analytically, so we have an exact estimate of what this parameter vector W should look like. Now we want to have a density for our parameter vector W, because this will then induce a density of predictions for which we can have our confidence bounds and so on. And we want to have this density of our parameter vector W conditioned on the data set that we have available. And employing the Bayes theorem again, we have that this posterior, this quantity we want to find, is equal to the likelihood, the bit that we calculated a few slides ago, times the prior, our assumption about the distribution of our parameter vector W, without having access to any data, divided by the marginal likelihood. So this is the likelihood, and we marginalize out our parameter vectors. And we are only left with the density of our labels conditioned on our observations X. And here we have this expression again. So the marginal likelihood, this bit here, is independent of our parameter vectors W, because we integrate this expression, so disjoint, over all possible parameter vectors W. And since the marginal likelihood is independent of our parameter vectors, we have that this posterior is proportional to the likelihood and the prior. So we don't consider the marginal likelihood anymore, because this will just be a normalization constant. We are now only looking at the likelihood and the prior, because they still depend on the weights. So again, the posterior is proportional to this expression. This is the likelihood, and this is the prior. So again, this is the likelihood. It's the exponential of -1 over 2 sigma squared of the squared magnitude of our error vector. So here we have our feature mapped observations X. We multiply it with our parameter vector. This will be our predictions. These are the true labels minus our predictions. Hence, this bit will be the epsilon vector, epsilon underscore. And epsilon underscore transpose epsilon underscore is the squared magnitude of our deviations. And we multiply this likelihood with the prior, which is the exponential of -1/2 times parameter vector W, the realization of the parameter vector W, transpose times the inverse of the covariance matrix for that parameter vector W times W. And from the lemma that we had on the first slide of this lecture follows that this expression is the squared magnitude of our parameter vector W, and this magnitude is parameterized by the inverse of the covariance matrix. Again, because this bit here is an inner product of W with itself. So we have the product of two exponentials where we consider the squared magnitude of our errors and the parameter vector W. And this looks like our empirical risk minimization, doesn't it? The larger they are, the lower this probability will be. And we have this regularization of our parameter vector W. And the larger the magnitude of our parameter vector, the lower this probability. And in turn, the lower the posterior of our parameter vector W, given the data that we have available. And since we have the product of two exponentials, we can combine these two arguments of the exponential and end up with this expression. So the posterior is proportional to the exponential of this bit. It's -1/2 times W minus W bar, which is defined below. We will talk about that shortly. Transpose, this bit transpose, times this matrix A, times this bit again, W minus W bar. And again, you can see that this looks like an inner product again, or the squared magnitude of this expression, W minus W bar, because we will look at these definitions shortly, but A is positive definite, and thus this expression will be the squared magnitude of W minus W bar parameterized by this matrix A. So what are those quantities? So A is equal to some constant times the uncorrected empirical covariance matrix of our dataset, of the feature map dataset, plus the inverse covariance matrix of our parameter vector W. And this object is just of dimensionality k by k. And we can see that A is indeed positive definite because we have this positive definite empirical covariance matrix phi x transpose phi x plus the inverse of another covariance matrix. And this is also positive definite. And the sum of two positive definite matrices is positive definite, and scaling them also leads to a positive definite matrix. So A is positive definite. And W bar is some constant again times the inverse of this positive definite matrix times phi x times y. And this is a vector of dimensionality k. We can write this posterior density as a multivariate Gaussian density, which is parameterized by this object W bar. And the inverse of A, this is the covariance matrix of this multivariate Gaussian density. And think about it, for a multivariate Gaussian density, you have the highest probability for the expectation, the mu vector essentially, and in this case it's W bar. This will be the mode of the posterior, and in Bayesian optimization lingo, we have found the so-called maximum a posteriori, the map estimate our parameter vector W. So we have found the posterior, this is this expression, and the most likely parameter vector to draw is this W bar, and it looks like this. And actually this most likely parameter vector W bar has a shape that should look somewhat familiar to you. Doesn't this look like the normal equation in a sense? Because we have the inverse of this matrix, and this matrix is phi x transpose phi x plus some regularization matrix times phi x times y. So recall the normal equation. We have that W star is equal to the inverse of this object. It's phi x transpose phi x plus lambda, the identity, the inverse of this times phi x times y. And here we have something very similar. We have some normalization constant. Let's forget about that. And here we have the inverse of this matrix A. And A is defined as some constant times phi x transpose phi x plus some regularization matrix. So this is this bit here. And we multiply the inverse of A with phi x times y. Phi x times y. So this is really analogous to what we have for the normal equation, but this time we have a posterior density. So not only a point estimate, this most likely parameter vector W bar, but instead this will be the expectation of our parameter vectors given the data set that we have available. But now we have a complete density for our parameter vector. And not only this one point estimate. So now that we have the posterior density for our parameter vector W, which is our belief about the distribution about the parameter vector W given the data that we have available, the x and the y, we are now ready to make predictions with our probabilistic model. So let's start with a single test observation. We will draw our prediction from another density that we will find shortly. It's this one. And to understand this density, let's first define this test observation, x star. It's one point where we don't necessarily have a label associated with it, this y star. And for notational convenience, let's define f star to be the prediction made by our parameterized model fw, given the input x star. It's the prediction for the test observation. Then we have that this density, the density of our prediction, given the test observation, the dataset that we have available for training, and the true label, y. And this density is equal to the integral where we average over all possible parameter values w, weighted by their posterior probabilities. So this is the bit that we dealt with on the previous slide. And we found that this was a multivariate Gaussian. This is also a Gaussian, this bit here. So the prediction given the test input and the parameter vector w. And if you solve this expression, so it's the product of two Gaussian densities, then you can combine the individual arguments to these Gaussians into one big argument of a single Gaussian, then you end up with this expression. And then we have that this random variable, which is our prediction for the test observation, given that test observation, the data set x, and the true labels that we have available, is distributed according to a univariate Gaussian density, because this is a regression output, it's a scalar, so it's a univariate Gaussian. And it is parameterized by this expectation and this variance. I know this looks messy, but let's have a sharp look. It will make sense in a second. So let's first have a look at this bit. So from the previous slide, we have that this is equal to sigma squared times this optimal parameter vector W bar. And this factor of sigma squared doesn't matter because we take the inverse of that at the front. So let's forget about this bit. It's the ideal parameter vector W bar. And then if you multiply from the left this phi x star transpose, then that's just equal to the inner product of this feature mapped test observation and this ideal parameter vector W bar. So our prediction F star is parameterized by this univariate Gaussian, where the expectation is this inner product, which makes sense, right? So you have the feature mapped observation X star and the ideal parameter vector W bar, take the inner product of that. This is our linear model formulation. And the variance of this Gaussian random variable is this expression. So we have A inverse, which was defined on the previous slide. It's essentially the inverse of the empirical covariance matrix given our data X, plus some regularization covariance matrix. And we have this expression where we multiply phi x star transpose from the left and phi x star from the right. And I hope you recall now that this, because this is a positive definite matrix, is an inner product parameterized by this matrix A inverse. And it's the inner product of these two vectors, and they are the same. So this is actually the squared magnitude of that feature mapped observation phi x star. And what this large expression tells you is we have this prediction. It's not deterministic as in the linear regression setup several lectures ago. This time it's a random variable. We draw it from a density. It's this density. And on expectation, we draw this prediction, which is the inner product of our feature mapped observation x star and the ideal parameter vector W bar. Ideal in the sense that this is the maximum a posteriori estimate of W given the data that we have available. This is our expectation. And since this is a density, this expectation comes with some uncertainty. And this uncertainty is parameterized by the inverse of the empirical covariance matrix of our data, plus some regularization covariance matrix. It's this bit here. And this matrix, which is a function of our input data X, parameterizes the magnitude of this observation, the feature mapped observation phi x star, and the squared magnitude given this parameterization of that observation that you put in as input for our prediction will be the uncertainty connected to our estimate. So the larger the magnitude of this feature mapped observation, the larger the uncertainty around our expectation. This magnitude of this feature mapped observation is parameterized by this inverse of the empirical covariance matrix, because in that empirical covariance matrix we have the information of how the features relate to another empirically. I hope this now makes a little more sense at least. But similarly to the situation we had in the kernel trick lecture, we now have an object of dimensionality k by k, where k is the dimensionality of our feature map, and inverting this object is infeasible. So it's the same situation as we had in the normal equation, where we had to find the inverse of this empirical covariance matrix plus lambda times the identity. And we used the kernel trick to arrive at a computationally more feasible formulation, which doesn't involve the inversion of this k by k object, but instead we had kernel matrices which were n by n, which might be more feasible if you have fewer data points than dimensions in your feature map. And it turns out that you can rewrite this random variable that we had on the previous slide, so the prediction given all these quantities, the observation for which you want to make the prediction, the data set that you have available at training time, and the true labels. And you can rewrite it as such, so it's getting a little more complicated even. But I want to draw your attention to this new matrix B, which looks like this. So it's the feature mapped data set X times the covariance matrix of our parameter vectors W times the transpose of the feature mapped dataset X. And this indeed looks like a Gram matrix, which we had encountered in the kernel trick lecture. So we have this situation again where we have phi x times phi x transpose, but this time in the middle again we have this positive definite matrix, which of course has some impact on the final shape of this object, but still this object satisfies all the requirements we had in Mercer's theorem. So this will be a kernel matrix. And now knowing that B is a kernel matrix, we will find that this is the parameter vector alpha star, which we had in our kernel formalism. And this bit here looks like part of a kernel matrix. So we have the phi x transpose on the right side, which turns it into an outer product. But since we only have the single observation phi x star, this will be a row vector, I think. Multiplying it with this column vector a star, which is the parameter vector in our kernel situation, where we reduce the dimensionality of the objects that we're dealing with, since we have access to these gram matrices. This, in turn, will be our prediction. And this makes sense, right? This is the expectation of our prediction. And it's the same as we had on a previous slide. It's the inner product of some row of the kernel matrix, and this parameter alpha star, which is equivalent to the inner product of the feature mapped observation and the ideal parameter vector w bar or star. So this is indeed equivalent to what we had on a previous slide, or the kernel trick lecture for that matter. And similarly, we can rewrite the variance parameter of this univariate Gaussian, but we will not deconstruct this now. So if you want to have a sharper look and find some expressions that you recognize from the previous slide or the kernel trick lecture, then go ahead, feel free. But let me just promise you that this is indeed equivalent to the variance formulation on the previous slide. So indeed, we have just rewritten the distribution of this random quantity, the prediction for this test input x star, where we got rid of this k by k matrix A entirely by exploiting these gram-like matrices B, which perfectly fit into our kernel formalism. We recognize some of it in this first argument of our Gaussian density. And similarly to the kernel trick lecture, we have that this object, where we also have this regularization term, is n by n, and it is more feasible to invert this bit here, because we need to invert it here and here, if n, the number of observations, is smaller than the numbers of features we have in our feature map. And I've alluded to this on the previous slide, kernels are back. So if you look at the expectation and the variance term in the univariate Gaussian density on the previous slide, you will see that we enter the feature space, which is defined by phi, exclusively in the form of these quantities. So we have this gram matrix-like object. We have some row of the kernel matrix, and we have an individual entry of the kernel matrix. So let me write it down. So here we have the full kernel matrix. It's the outer product of phi x with itself. And in the middle we have this positive definite diffusion covariance matrix, sigma w. This is an n by n object. Then we have this quantity where we multiply a single observation from the left, and this will be an individual row of a kernel matrix, where we compare this phi x star with all the entries we have in our data set. And finally, we have the inner product of this feature mapped observation x star with itself, which is then the squared norm of that observation. And recall, in the kernel matrix, we store these inner products. So this is a individual entry of the kernel matrix. And no matter which of these objects you investigate, individual entries in these objects are of the following form. It's the inner product of some feature mapped observation with another feature mapped observation. And this inner product is parameterized by this positive definite matrix sigma w. This will be the evaluation of a kernel function given these two observations. And xi and xj could either be in the training set, so this capital X, or it could be in the test set, so this x star, which consists of only one test observation. Hopefully by now you believe me that indeed these inner products parameterized by this covariance matrix sigma w relate to evaluated kernel functions. But maybe it's annoying to you that we have the sigma w in the middle of all these vector multiplications. But this is really no issue at all, because sigma w is positive definite, as it is a covariance matrix. And since it is positive definite, we can find the square root of that matrix, and it is defined as such. So multiplying this square root with itself should yield this matrix again. And again, such an object exists, so you can always find the square root of a covariance matrix. And now let's define a new feature map of our observation. This feature map will be psi, and it will be defined as the square root of the covariance matrix times the feature mapped observation with the feature map phi. And with this new feature map, we obtain the inner product representation that we got to know in the kernel lectures. So the evaluated kernel for observations xi and xj is the inner product of two feature mapped observations xi and xj with the new feature map psi. And this is the inner product for the reproducing kernel Hilbert space h-tick. So at this point I have to admit that I'm not even sure if this is the same reproducing kernel Hilbert space induced by the feature map phi this would be just 8 because we just have this linear mapping in front. So maybe it's the same actually. So I'm not sure. I haven't investigated this, to be honest. But if you feel like you can answer this question and provide a proof, then go ahead. I'd be happy to know, actually. So consider this a bonus exercise. And then I have this proof that finding the square root of the covariance matrix sigma w suffices to define this inner product and resolve this issue of having this covariance matrix in the middle of these vector multiplications. It's really trivial. Let me write it down. So this was the starting situation. We had this vector multiplication with the covariance matrix in the middle. So this was maybe annoying to some of you, and we found a way to still end up with a proper inner product. And since this is positive definite, we can decompose it into the product of these two square roots of that object. And we have that this bit here is just psi xj, as we defined on the previous slide. And this bit here is just a transpose of the feature map psi, because if you transpose the feature map psi, then the bit with the feature map phi goes to the left. You transpose it, so this is what we have here. And the covariance matrix goes to the right and is also transposed. But since this is symmetric, we don't need the t explicitly, and we are left with this expression. And then we have psi xi transpose times psi xj. And this is just the inner product of these two feature map observations for the feature map psi in the reproducing kernel Hilbert space induced by these feature maps. Now in this lecture about Gaussian processes, we haven't started talking about Gaussian processes yet, but now we will do so. So let's define a Gaussian process. And a Gaussian process is a potentially infinite collection of random variables such that the joint distribution of every finite subset of these random variables is multivariate Gaussian, right? Okay, so you have this collection of random variables. It's a set. If you take any collection of random variables from that set and you find the joint density of those, and for all these joint densities, you find that this is a multivariate Gaussian, then you have a Gaussian process. And you are guaranteed to have a Gaussian process if your collection of random variables is a collection of multivariate Gaussians, right? Because if you take the joint of two or more multivariate Gaussians, you have that this will be, again, a multivariate Gaussian. And this will then satisfy this definition. And note, a Gaussian process is completely specified by its second order statistics. So you need the mean of the Gaussian process and the covariance matrix. And we will define this mean as follows. It's a function of an observation x, and it's the expectation of our predictions. Again, our predictions are random variables for that observation x. And for this covariance, we take this kernel function for the observations xi and xj. It will be the covariance for our predictions for observations xi and xj. And the covariance is defined as this expectation. So it's the expectation of the product of the realization of our prediction minus the expectation of our prediction for both observations xi and xj. So these are the parameters for our Gaussian process, and we will write the Gaussian process as follows. So this random variable, our prediction given the input x, is drawn from the Gaussian process gp and is parameterized by this mean function m and the kernel function k. So now I want to convince you that Gaussian processes are not new concepts that are unrelated to what we did before. I want to show that the Bayesian linear regression that we build towards in this lecture is a Gaussian process, right? And for this we had that our linear model is this bit here. It's the inner product of our feature map observation x and a parameter vector w. This parameter vector w comes from a prior distribution where we don't have access to observations x and y. And this will be a multivariate Gaussian density with expectation 0 and a covariance matrix associated with this parameter vector w. And now, without loss of generality, we assume that our prediction is zero-centered. This means that the expectation of our prediction, which is the expectation of this inner product, is 0. And we can push the expectation into this inner product, into both arguments, because the inner product is linear. But we find that the feature map observation x is a constant because x is already realized. So it's not a random variable anymore, but w is, right? So we have this expression here. The inner product of the feature map observation x and the expectation of our parameter vector w is 0. And we make this assumption to simplify the following calculation. So let's find the covariance function. It's the kernel function for observations xi and xj. And since this is the covariance of our predictions given these inputs, and we assumed our predictions to be zero-centered, we have that this covariance simplifies nicely to this expression. So it's the expectation of the product of these two predictions for inputs xi and xj. Both of these predictions are inner products. And then we can just push in this expectation into the inner products because the inner products are linear mappings. And we are then left with this product of two inner products, where the first argument of the inner products are the feature mapped observations. And the second one is the expectation of our parameter vector w. We have that for both inner products. And then if we just write it out as vector products, we have this expression. And here we use linearity of the expectation to arrive at this formulation, where we now have the expectation of the outer product of our parameter vector w with itself. And this turns out to be the covariance matrix, sigma w. Now we have the inner product that we found on the previous slide. So it's the inner product of feature map observations, xi and xj, where the feature map is psi. Okay, so why did we do this? We have that these two random variables, the prediction for observation xi and prediction for observation xj, are jointly Gaussian. Because the joint of these two random variables, they're both Gaussian, is Gaussian. So they are jointly Gaussian. They have zero mean. So this by construction without loss of generality. And we have this covariance matrix, which was the inner product that we found quite naturally for our Bayesian regression setup. And all of these findings from the Bayesian linear regression that we did suffice to define a Gaussian process. So the Bayesian linear regression that we did is a Gaussian process because we have a mean and a covariance function. And what you can also show is that any collection of predictions for a number of observations xi is jointly Gaussian if the number of observations that you're considering is smaller than the numbers of features in your feature map. Or more technically, any collection of such predictions is jointly Gaussian. But if we have more points to predict than we have features in our feature map, then this joint Gaussian will be singular, which means it will concentrate on a point mass. There will be no variance. This is a technicality you don't have to worry about in practice because you'll be using infinite dimensional feature maps anyway. And since you have finite points to predict, this will never be the case then. So again, to hammer down, the idea on this slide is we did Bayesian linear regression in the beginning of this lecture. I then introduced Gaussian processes as a new concept, but what we found for the Bayesian linear regression suffices to define a Gaussian process. So this Bayesian linear regression that we did is indeed a Gaussian process. So in the lecture about the kernel trick, I showed you a few valid kernel functions, and this is one of them. So we talked about the Gaussian kernel. It maps into an infinite dimensional feature space. And let's use this Gaussian kernel as our covariance function. So the covariance of our predictions for two observations, xi and xj, is a kernel function. This kernel function we define to be the Gaussian kernel. And the Gaussian kernel is the exponential of -1/2 times the squared magnitude of the difference between the observations for some magnitude. So you can go for any magnitude, and since we are considering finite dimensional observations, I guess a natural magnitude would be the squared L2 norm. Now observe that the covariance between the predictions for these two observations is given as a function of the inputs and not of anything else. So we don't need the parameter vector, we don't need the shape of our model, it's just the data points. And this is important because it says the degree to which our predictions vary is only determined by the observations that we put in. And also, since we assume our predictions to be zero-centered, specifying this covariance function is enough to define a Gaussian process. And since this is a density, we can draw samples from this Gaussian process. And what's interesting about the Gaussian process as compared to a multivariate Gaussian is, for the multivariate Gaussian, you get a vector. But with a multivariate Gaussian process, you have this collection of random variables, possibly infinitely many. And if you draw an individual sample from this Gaussian process, you draw a prediction model, right? So we draw prediction models from the Gaussian process, not predictions. This is important. Okay, so previously we produced predictions for individual points. But this time, we want to make predictions for a test set, X star. And this test set contains n test many entries, and every entry is one test observation of dimensionality d+1. So that's prior to applying the feature map. We can now construct the corresponding kernel matrix or covariance matrix, which is of dimension n test by n test. And each individual entry is the evaluated kernel function for two test observations. Okay, what we're going to do now is we will draw from the prior distribution. So without any information about the training data set that we had available, so the x and the true labels y. And we draw such a prediction vector, which is of dimension n test. We want n test many predictions, one for each point. We draw this prediction vector from a multivariate Gaussian, which is again zero-centered, so the expectation is the zero vector. And this multivariate Gaussian is parameterized by this covariance matrix. But again, this is a draw from the prior distribution. And in the Bayesian framework, that's not the distribution we're interested in. We are interested in the posterior distribution. And we arrive at the posterior distribution by including the information our training observations provide into our model formulation. Okay, so first we study the case where we make a simplifying assumption. So our training observations, the dataset that we had available, we consider to be noise-free. So the measurements we did regarding our features and our true labels, they are without any noise. They are perfect measurements. And if we then apply Bayes' theorem to arrive at the posterior, given the prior that we defined on a previous slide, we arrive at this statement. So the random variable, our predictions for the test observations, given the test observations, the training data set, and our labels for the training data set are drawn from a multivariate Gaussian density, where the expectation is this expression, and the covariance matrix is this expression. And this expectation vector kind of looks like the normal equation without the regularization term, right? So we inverse this empirical covariance matrix, and although we don't have the x, y on the right side, only the y, we have that x on this left side, so that the dimensionality makes sense with regards to this kernel matrix. The details are not really important. The main intuition I want to bring across is that this is again a quantity that is somewhat intuitive. It's the most likely prediction given our training data. And it happens to be that the most likely solution to the regression problem is the same as the one that we arrived at when we were minimizing the quadratic error under some modeling assumptions. Namely that the errors epsilon are IID distributed according to a univariate Gaussian density. But now let's have a look at this covariance matrix. So it consists of two parts basically. So this is the covariance matrix for our test observations. It's the statistical relationships between these observations. And in that we measure the uncertainty associated with the test observations. And by conditioning on the training data, which should provide us with some information about the relationship between inputs and outputs, we're able to subtract uncertainty from this covariance matrix. So it's the inverse of the kernel matrix of our data. So that's essentially the information that we gain by having a training data set. And we have these two connecting vectors that transform this information into the right dimensionality so that we can subtract it from the uncertainty associated with the test observations. So now I think it's time to show you actually what Gaussian processes look like, because we've been talking about them formally, but images speak louder than words. So let's have a look at this illustration. So let's first look at this plot. It's the prior distribution of our Gaussian processes, or our Gaussian process predictions, actually. Let's first study this gray area. So the plot description tells us that this shaded area is the 95% confidence interval for our Gaussian process predictions, and they are zero-centered. So for any given input x, we produce a prediction. These are the dots, and we draw these predictions for a number of inputs, as many as we want, and in the limit, they will form a continuous function, and this is what these plots then represent. So essentially each draw from our Gaussian process is one of these functions, and from an implementation point of view, it's that we generate these individual predictions and they will form such a mapping, a continuous mapping. So this shaded area tells us that on expectation 95% of these lines, our functions, will be within this shaded area. Sometimes it will leave the shaded area, but not really off, because this is the 95% confidence interval of our Gaussian process samples. But this is the prior, the less interesting case, because we don't take into account our training data. So now let's look at the posterior. So we have these 4 training points for which we know the label. So for this point, we have a training label, and it seems to be 2. For this value, we have something around 1. For this value, we have something around 0. And for this value, we have something around -2. And conditioning the Gaussian process on these observations leads to this shaded area. So we condition our draws from the Gaussian process so that they have to pass these observations for which we know the truth. So all other functions that don't pass these points are just incorrect. We know this by conditioning on our training data. But for the intervals between two observations, there's still some uncertainty because it could be many functions that go from this point to this point. So this is why we still have the shaded area. But now you see that the shaded area has some meaning to it actually. It's not just a flat line. So now it's sausages or tubes around our Gaussian process samples. And what we can see here for the endpoints is if there are no points left to which you could draw from our edge points, then the uncertainty just increases because we don't know whether an empirical point would be here, for example, or down here. So our Gaussian process model accounts for this by expanding this uncertainty region. Also here on the left, you can see that it extends quite quickly. So on the previous slide, we have seen a case where we considered our training data to be perfect without any noise. So our Gaussian process density was conditioned so that we could only draw functions that pass these training points. But assuming that our training data is noise-free is an unrealistic assumption. So let's include noise into our model formulation. We have these epsilon terms. Also recall that we assumed these epsilon terms to be IID distributed according to a univariate normal density with some variance sigma squared. And with that we have that the covariance of two labels, yi and yj, is equal to the evaluated kernel for two observations xi and xj plus sigma squared times this Kronecker delta. So the Kronecker delta is equal to 1 if these indices I and j coincide, and it is equal to 0 if the indices disagree. And we have this Kronecker delta because for observations that coincide, we add the variance term associated with the error. And if two observations don't coincide, we don't want to include the variance of our errors because they are IID. So this is the reason why we have this term here. Observe that this is an individual entry of our covariance matrix sigma y. And if we were to write it down for each possible combinations of inputs, we have that sigma y is equal to the kernel matrix of X with itself plus sigma squared times the identity. And this shouldn't look surprising to you because, again, it looks like the empirical covariance matrix plus some regularization. So X transpose X plus lambda times the identity. We have seen that in our linear regression several lectures ago. And this is what we also have here. Okay, so to recap, we introduced noise into our model formulation, and we want to now find the posterior again, this time with the noise included. And actually it's very straightforward. We just have to add this regularization covariance matrix, this sigma squared times the identity, to the parameters of our model. So more formally, we have this random vector f star. This is the vector of predictions for our test observations, conditioned on the test observations, training observations, and the true labels at training time. This is distributed according to a multivariate Gaussian density, parameterized by this f bar star and the covariance matrix sigma f star. And let me give you the definition of these objects. It's what we've seen before previously, but this time we don't invert the kernel matrix of X with itself again, but instead we add this regularization covariance matrix sigma squared times the identity before inverting. And again, this looks like the normal equation where we have a regularization term again. And the covariance matrix also looks similar again. So we have the uncertainty inherent in our test observations. And from that, we subtract the information that we gained by having training data. This time we don't invert the kernel matrix of X with itself, but instead we invert this quantity where we add to our kernel matrix X with itself this regularization covariance matrix sigma squared times the identity, which effectively makes this matrix larger, this covariance matrix, and then we invert it. And with that we reintroduce a little bit of noise again, a little bit of uncertainty, because we can't be sure, since we have noise in our measurement, that the labels that we draw from our Gaussian process correspond to the training labels we had available. So again, recall that on the image we had that all samples we draw from the Gaussian process had to pass the training points. But with this regularization term, they are now free to not pass the training points. Of course, the uncertainty around the training points will be smaller than for regions yet unexplored, but still this allows our model to not overfit to the training observations. But again, the structure is similar again. We have uncertainty associated with the test observations. From that, we subtract the knowledge that we gain from our training observations, but not to blindly trust our training observations. We include this additional uncertainty, which will make this information gained by training a little less impactful. So we are left with more uncertainty associated with our test observations as compared to the noiseless case where we didn't have this regularization term. So I want to conclude this lecture with some illustrations about varying the hyperparameters associated with our Gaussian process model. And you deal with these hyperparameters when defining the kernel function that you need to construct a covariance matrix. And if you go for a Gaussian kernel, you could have 3 of these parameters. So the first one is the noise associated with the measurement. So we've dealt with that on the previous few slides. It's the uncertainty around our measurements. Then we have this signal variance that we multiply our exponential of the negative between the difference of 2 observations. And we have the length scale L, by which we divide the squared difference between these 2 observations. They're univariate. This is why we only have the square and not the norm of the difference between 2 vectors. So let's first look at this parameter, the measurement noise. So we see that for this first illustration, the measurement noise is 0.1. So this means that this impact is relatively small. And we see that this random draw from the Gaussian process passes, roughly at least, our training observations. But if you look sharply, for example, at these 2 points, this draw from the Gaussian process doesn't pass these 2 points exactly. It's just a little off. If we look at the second illustration, where we have a much smaller noise parameter, you see that the model makes an effort to really pass through these points exactly, and it turns out more wiggly. So this looks somewhat like the overfitting case that we had several lectures ago. And finally, if you crank this value up like a lot, then your model doesn't even try properly. So you see you have a lot of flexibility in how much you want your draws from the Gaussian process to pass through the training points you have available. And you tweak this by thinking about how sure are you that the measurement is accurate. So in physical experiments, I would be relatively sure about my measurements if the measurement tools are calibrated correctly, as compared to psychological or economic studies, where you have more inherent noise in your measurements because the phenomena that you study are a little more abstract and less concrete than in physics, for example. So this heavily regularized function might be just what you want, or you might be more interested in having such a draw from your Gaussian process, which really honors the data points you have available. Now for these other hyperparameters, the length scale and the signal variance, I'll leave it to you as an exercise to study these illustrations and make sense of them. But this will conclude the second to last lecture. And next time we will talk about the relationship between kernels and Gaussian processes. And this will actually conclude this module. So see you next time for the final lecture of this module.